the today's discussion. So, where in the last part of this particular discussion, as we talked about the real-time operating system, its differences with the general purpose operating system, and few services that already being discussed about how this RTOS would offer the service differently. And the offering of this service differently is in order to offer the constant deterministic and a priori service time, which definitely helps to build up a predicted system, which is what we referred as an real-time systems. Okay, so again, the part two discussion of last time or last session that we are going to have today is all about few of the services like dynamic memory management, like we have discussed RTOS, why and how. We have discussed the differences of this RTOS and GPOS on a functional level, on the conceptual level. We also understood what are the different typical components of RTOS and its related inputs or related, or I would say associated kind of inputs those would require to this real-time components. And we'll see that we have seen that how does RTOS would offer the services in order to give the constant a priori known service time. We have seen few of the mechanism, service mechanism by the RTOS, where we have seen the task management service. Okay, we have seen the interprocess communication service, and we have seen the timer service of it. And we have seen that how these particular services are offered in order to offer a constant a priori known service time. So we'll see today how does this RTOS would believe, or how does this RTOS would offer this dynamic memory management service, and how would be different it from the GPOS. Then we'll see few of the or very typical approaches those are being taken for real-time scheduling. We are going to discuss the approaches at the moment. Okay, so maybe in the next discussion when we are going to discuss about the MUCOS 2, there we'll have some example scheduling mechanisms, how that they are going to help out into the designing or building up the real-time system. So in the today's discussion, we'll restrict our discussion only to the approaches for the real-time scheduling. Okay, and then we'll just conclude on whatever we are supposed to take away out of this particular discussion. Fine. So moving ahead, as we've seen, the dynamic memory allocation is a service that is being given from operating system in order to manage the available memory between the different resources and tasks. This is what we know the functions of the memory manager in any of the operating system. Okay, so in relation with the embedded system or in relations with the real-time system, being a part of embedded system, once again, we understand that when the execution of an application gets executed on paper prior to getting executed onto any platform, that means in design of such kind of system, there incurs or there involves heavy determinism, isn't it? So this determinism involves even making use of the memory for the different tasks or different resources which are being used into the application. So having said this, we have enough reasons to believe at the moment that in designing of the embedded system, we have a mechanism which is strongly believed to be as a static memory allocation. If you saw the earlier examples that we have executed in the practicals, you might get to know that the task is being offered with a stack, a private stack. And these particular stacks were computed before the task gets executed. This is an example, like how do we allocate a static memory to the different tasks those are being involved in the application, even though with the help of operating system. But many times it so happen that in the available memory, the application designer has to cater the requirement of the memory. And in that particular case, you cannot go with a static allocation methodology because you might not have the luxury of heavy memory to allocate statically, that is permanently to a specific task. And there it comes the role of memory management into the embedded systems. If you understand this particular basic concept, like why memory management would be required specifically in embedded system, the reasons are again not different than what is being there even for the general purpose system also. Okay, the reasons are the same. But we have seen that when allocating a memory dynamically in general purpose operating system, it leaves out the many traces, and these particular traces, as we refer to be as in fragmentations. In the last chapter, we have discussed the basic drawback of or virtual memory allocation in this particular operating system that suffers from the fragmentation. So even though memory is being available in the chunks, even though the volume of memory is being available for the application, that cannot be made use of because the contiguous part of the memory is not available for a specific task. And then there comes the solution, remedial solution that we call as a garbage collection. We are building up the logical linkages among the fragmented memory blocks in order to offer that to the for the task to get it execute seamlessly. That is what the job of this particular garbage collection approach or the garbage collection application, which is the remedial solution of this particular fragmentation. So this is what we known from the ages for the general purpose operating system, and even real-time operating system. This would also be true if the fragments are getting generated out of it. Okay, but in real-time system, generation of the fragments, or if the memory undergoes with the fragmentation problem, then there will not be much solution that is to be done with it. Because we know that most of the embedded systems, most of the real-time systems are mission critical systems, where failure of the system is not accepted. Even tolerant of the system is to be offered with some degree of relaxation, with some degree of adaptability. And that is what the sole reason that why these embedded systems are basically believed to be as in statically allocated memory systems. Okay, but in case, as we discussed earlier, that if there is no alternative rather than going for dynamic memory allocation, then we have to think on, or the operating system has to cater the services in different aspect than the general purpose operating system. And the different aspect is not to get caught into the garbage, not to get caught into the fragmentation problem, so that the reliability, or so that the determinism of the application, that would not be compromised at any point of time in the execution. This is what the way in which the RTOS has to offer this particular services to this application, which would be different than the general purpose operating system. Means RTOS has to be more careful, has to be more cautious to get believed or to get confirmed that fragmentation would not occur out of this particular memory allocation process, even though it is a virtual or dynamic memory allocation. Okay, so as we have discussed on the preamble, we can see a few of the points in a very quick fashion. That many, as I said, many, but not all, RTOS kernel provide dynamic memory allocation services, because this is not referred to be a very essential service of the RTOS. Okay, this can be written on top of this particular microkernel approach to just build for that application specificness into the system. Okay, then this category of service allows tasks to borrow chunks of RAM memory for temporary usage in application software. This is what general feel that we even know for the virtual managers of GPOS also. The same thing that is being offered. These chunks of memory are then passed from task to task as a means of quickly communicating large amount of data between tasks. Okay, so when we are believed to be an IPC with a shared memory, or when we are believed this IPC to be through this particular transferring of the memory block itself from task to task, this particular dynamic memory allocation service would be helpful definitely in a way. Okay, then very small RTOS kernels that are intended for tightly memory limited environment do not offer dynamic memory allocation service. This is what we were talking about. Okay, so it's not mandatory for all the RTOS to cater the service of dynamic memory allocation. But if being offered the dynamic memory allocation, what should be the way in which this particular service to be offered? That is what the matter of discussion henceforth. Okay, so let's see that how does it offers. Many RTOS has memory management subsystem, as we say. Okay, then as we know that the C functions like malloc and free do the memory management, but many RTOS avoid using this because of their execution times are unpredictable. And when any execution time becomes unpredictable, that is basically a hurdle, or that is basically a glitches in designing the predicted system or a real-time systems. That is what this malloc and free is generally not being used in RTOS. So instead of this malloc on free, what kind of strategy that can be used for it? So this RTOS would sets up the pools, the memory pools, each of which consist of some number of memory buffers. In a given pool of buffers are of the same size. We'll see the logic behind it. Okay, in a memory, like we know there is a concept called the concept of paging in virtual memory that we saw the last time only, last unit only. Okay, so similar to that, the mechanism by which this RTOS would offer the dynamic memory allocation is it sets up the pool of memory. Okay, and in each of the pool of the memory, there would be some buffers. And these particular buffers are to be of a same size. This is the strategy that is being used. Why it is of same size? That would be understood in a next slide with a proper diagrammatic representation of it. At the moment, just believe that it is of a same size. With what kind of advantage that we'll have, we'll get to know it very soon. Okay. Then the request buff and get buff functions allocate the buffer from the pool. So whatever the memories that you are defining into the memory pools, this particular two functions, request buff and get buff, those would get allocated the buffer from the pool. Each returns a pointer. This is very interesting and very important. Each would returns a pointer to the allocated buffer. If no buffers are available, then get buff blocks the calling task, whereas request buff returns a null pointer. Now, request buff is basically, as we know, that malloc service is there. Okay, so before that, there is a request that is being made from application to the memory manager about the amount of size or amount of memory that is being required for that application. Okay, then there is a calling of the malloc kind of functions. Likewise, there is a request buff is a function that expect the application that is expected to be called from application programmer to an operating system requesting this specific size of memory to be used or to be allocated for this particular task of it. Okay, so and after that, whatever the if that is being sanctioned, when that would be sanctioned, that would be sanctioned only after the operating system memory management module would check the availability for the same. If that availability is being found, like for example, if any task is being demanding, for example, 512 KB of memory for execution time temporarily for that particular task. So the very first thing that it would do is by the request buffer. Okay. Then in response to that particular request buffer, the RTOS memory manager service, what it would do, it would try and find that is there any of such buffer is available in which pool of the memory that is being divided. If it is being found that in that particular pool, the memory is being available, then it would give the pointer, it will give the pointer to that particular task. And that particular task through that particular pointer will demand that particular amount of memory to the memory manager with the API called as a get buff. That is called get buffer of the expected size of it. Okay, if that is not being available, then the get buff blocks the calling task, the task from where the get buff is being called, that task, because memory is also resource, and if a specific resource is not being made available, then we know, the as per the theory of the RTOS, we know that if this particular specific is not being available, then the calling task has to get blocked, because it cannot keep waiting for free memory of that 128 bytes, for example, to be made available, and then the task would get executed. By that time, the utilization of the CPU that would be gone very low to that, and we cannot afford to go utilization of the CPU less than that of 50% at any point of time in the real-time operating system or the application that gets built onto the real-time operating system. Isn't it? So looking onto all this consideration, these memory managers even can be thought of one of the mechanism of task switching. We are seeing different mechanism of task switching, right? So along with that, this particular memory manager, when RTOS functions are getting called from the application task, being not satisfied in a judicious way, the calling task might get blocked, right? And when task get blocked, it gets into the waiting list. Okay, and then after the turn, after a specific time, or in this particular case, when that particular memory would be available, the memory manager would give an indication that memory is available. So the resource for which it was waiting, there will be no more any time. So that particular high priority task would be there in a ready queue. And if that is high priority, then it definitely going to be an executed one. So this is again all the cycles that is being happened with the state transition of the task, even with the help of this memory management service also. Okay, this is also one of the point that is to be expected to be understood at this particular moment. Okay, fine. Now, after the job, after the task finish off, making use of the allotted services, like we see that there is a function called free into this memory manager, okay, or memory heap service of this operating system. Likewise, we have the service called rel buff, that's called release buffer. The buffer that is being taken, it is to be released back to the memory manager. Okay. So once it gets this particular release, execute this calling function executes the release buffer, it frees the memory which is being allocated to it, so that that particular memory could be given back to this. So is there any fundamentally more difference into the way in which this particular services are getting offered? The way in which this particular services are getting offered is one and more same. Then what guarantees that it will not get an unpredicted time, or it will not get the fragmentation problem for embedded systems? Because embedded systems cannot afford to have all these kind of problems. And the answer to this particular question, let's understand it through the next slide of it. The arrangement or the mechanism that is being built up into this dynamic memory allocation in RTOS is, you can see that this particular memory pool is maintaining the free buffer lists. Like you can see that right from this particular 0 to 31, 0 to 63, 127 means 32 bytes, 64 bytes, 128 bytes, 256 bytes. So in that increasing order, that particular buffer sizes are being there into a memory pools. Okay. So memory pool maintain this particular size. Okay. And then whatever the task that is, expect that particular memory to be borrowed, a chunk of task that memory borrowed, it will not borrowed in the pages. It will borrowed in the form of the available memory, or in the form of the required bytes of it. Okay. And as the different pools has got the different bytes, it is very easy for that memory manager to understand where does the pool do have an unoccupancy of the memory, or do have the free of the memory. So it puts up that particular free memory into this free buffer list. And once the free buffer list is being populated, okay, the memory manager serves onto that, or memory manager transfers onto that free buffer list and gets to know from where it has to be offered. And that's what pointers are getting passed onto it. Okay. And it's a very interesting and beautiful aspect of it is, once the task gets used of this particular memory, the pointer is being passed, right? So the same pointer is expected to be returned back to, same pointer is to be expected to be returned back to the memory manager, so that memory manager gets to understand where to make this particular freed memory from the application, in which pool it has to be transferred, in which pool it is to be allotted. Means there is a very high confirmation, there is a degree of confirmation is very high, from like the pool from where the free memory is being allotted. Once that particular memory usage is being made from the task, that particular memory chunks would be allotted, that particular memory chunks would be transferred back to the same pool with the same amount of memory as in buffers. If this is being happened in the so deterministic fashion, then let me know that where does the indeterminism, or where does the non-determinism would come into the picture of the, in this particular fashion, if the memory is getting allotted. And this is what referred to as a foolproof mechanism of memory allocation in RTOS, which guarantees the service, even the service time also guaranteed to be as an heavily deterministic. And this particular deterministic time would definitely be helpful in building up this particular uh, in building of this particular determinism into an application of it. It's as simple as this, right? I think you now understood like how this determinism is being built, or determinism is being offered in memory allocation in the RTOS, because RTOS is being used for embedded systems, real-time systems, and that cannot afford, as we discussed earlier, the fragmentation issues and all that cannot be offered, or that cannot be afforded at all. Getting it? So with this particular discussions, I think like most of the things that you are trying to understand out of this particular dynamic memory allocation in RTOS, that particular concept might have been clear to you. Okay, we are going to perform an experimentation based on this also. Okay, the reference from where I have taken all this literature and I'm discussing out this particular literature is the mentioned link for the one of the white paper, which makes it very clear concept about what is the differences of services, in what way these particular services are to be offered to build up the deterministic service time. Okay, so I expect that this particular link which is being given, that would be made use. Okay, or in order to understand, or in order to reinforce the understanding that you are currently going on with it. Okay, fine. So this ends up with the memory allocation discussion into this RTOS. Fine. Okay. So moving ahead further, in addition to what your services, those we have discussed, as we know that most of the RTOS services are being a microkernel in nature, or more of the types of the RTOS that got built is of a type of microkernel. Okay. So as we know, only essential services would be the part of kernel. Okay, and other services would be on top of it. So what kind of other services might be required in the RTOS also for building the real-time systems in addition to the basic set of services? So these services might go with some kind of file system organization, file system management. Okay, so in the next section of this particular course, where when we are going to discuss about the Linux, more specifically an embedded Linux, then as being Linux being a complete file system, the different file systems are being used in embedded Linux applications. And that is an interesting proposition to understand. How does the organization of this particular data in a file in order to ease the embedded applications to transfer or to store the data even into the different hierarchical formats of it. So that kind of service would also be expected to be designed and included into many applications that might be used for this RTOS. Okay. The second set of services, as we know, that network communication. Needless to say that nowadays no device can afford to be a standalone. Every device is expected to be there onto the network. And in this particular situation, maybe the current RTOSs which are being there in the market today, they might not exclude the network communication as a service. They might treat this particular service to be as an essential service. Okay. So network communication, as we say, the by virtue of giving other services in the different protocols, network protocols on which your embedded systems are supposed to get built up. Okay. So these particular services would also be there as a part of RTOS. And that in the current trend, it would become a de facto standard of it. That is what my personal belief goes on. Okay. The network management, that also would be one of the very interesting service that is expected to be there within RTOS in line with the network communication aspect of. Then database management, that also would be required very heavily nowadays, right? And the user interface graphics and all, if that is being required as an optional services, that even also can be built up onto it. Okay, but there is a heavy contradiction that occurs into it. Okay, so when I'm saying it's a user interface graphics and all that, okay, if that those particular service gets into or that requires some human intervention, then that real timeness is not being maintained at all into it. Because the most unpredicted contribution or the most unpredicted events that can be referred to be as a human intervention. Because humans are referred to be as a most unpredicted entity on the earth. That's what when the intervention comes from the human side, then better not to refer that system to be as in real-time systems. Okay, fine. These are the additional set of services that might be required in the RTOS. Now, quickly we'll go with the different commonly used approaches for real-time systems. Okay, and this for real-time scheduling specifically. So these particular common approaches are expected to be understood, because unless these approaches are not being understood, there will not be a proper selection of the approach. If approach is not being properly selected, the related scheduling mechanism which adheres to that particular approach, that might not got selected in consequences, and as a result of which there is a heavy fear or the great fear that you might not attain whatever you wanted to have as a timeline or the deadline achievement in the application. So importance and significance of having this approaches to be understood is very tall order. Fine. So let's try and understand very simple kind of approaches those are being used. Is first one is a clock driven approach. Okay. Second one referred to be as a weighted round robin approach. And third one referred to be as a priority driven approach. These are the three approaches. These are the three kind of systems in building up the scheduling algorithms of real-time system design are being more commonly used of it. Okay, that's what we are using the word commonly used. So let's see it one by one. I think from the name itself, it is very clear that what this clock driven might be. Okay. So in this clock driven, we know that the activities are being scheduled well before of its execution on its timeline. In a simple one statement, if I want to narrate this clock driven approach, then activities which are expected to be executed, those are being well scheduled in line with the time. Means it's a clock driven. At a specific instance of time, this particular activity should get scheduled. At second instant of time, this activity should get scheduled. I mean, this is a simplistic approach that is being used in RTOS if everything goes on deterministic level. Okay, so if you're building an application which has got a heavy dependency among the task or heavy dependency of the resources for that particular task, then this particular clock driven approach might not be suitable for design of that particular systems. So let's discuss it very shortly what this clock driven approach is all about. Okay, so as the instance are chosen a priori before the system begins its execution, as we have seen it, then schedule of the jobs is computed offline and store for use at runtime. This is what we say it's in clock. Like if I have got 5 tasks, then at what point of time the task 1 to 5 is getting executed, that is being computed or designed at the offline. Okay, and this stored schedule is being made use in the runtime by the scheduler in order to schedule those kind of activities of it or schedule those kind of tasks for it. So this approach seems to be very simple. So scheduling overhead during the runtime can be minimized. This is an completely new dimension or the simplistic approach, but it would not bring up a lot of determinism for sure. Okay, because for a simple real-time systems where you don't occur or when you don't depend on many heavy resources, intertask communication, maybe the resource synchronization or the less resource dependencies being there. So that kind of approach is definitely, or that kind of systems would definitely getting driven by this particular clock driven approach. Means everything is being completely certain. Okay, so that kind of certain activities can be scheduled on the clock if no dependencies are being found onto it. Okay, so these, and that is what is being said, that runtime scheduling overhead, because whenever the scheduler tries to find out the priority to be executed next, it occurs its own services to be, like we have seen that it transfers to the task control block with the whether the state of the task, priority of the task. So in doing so the scheduler invests its time, and that time, as it not contribute to the functionality of an application, it's a service time, it's not contribute to functionality of the application, we refer that time to be as an overhead time. That is the scheduling overhead time. So in clock driven approach, this scheduling overhead time is heavily minimized because scheduling overhead during the runtime can be minimized. Then scheduler that makes scheduling decision periodically is to make use of the hardware timer, for example. So hardware timer can be made use of, and you can make use of this particular scheduling approach for it. Okay, it's as simple as this. So with the time expire event, scheduling is instantiated. So at what point of time the next event, next task is to be scheduled. So once the first task timer is being elapsed, timer is being expired, then the scheduler gets to know the second task is to be scheduled. As simple as this. Okay, that is what referred to as a clock driven approach. Simple. For simple applications, this approach might work very well. Okay, there is nothing, no attempt is to be made to hit the mosquito with a bazooka. Whenever system demands a simple approach, that has to be there at its own place. Getting my point? So it's completely boils down to, if someone asks like which kind of scheduling algorithm, no answer at all, because every system is different. Every system's requirements are different. That's what we say, that in embedded system or real-time system, there are no rules for it. It's only derived by the guidelines. Getting my point? And that is what it needs, an experience to be catched up in order to be matured in the field to be referred as an professionals onto it. Okay, fine. So the next approach that we would understand is the weighted round robin approach. Now, I think round robin approach is very simple, and that we are talked of when we discuss the software architecture also, isn't it? So in round robin, we know that we have the priority of the tasks which are being fixed. Okay, and we have got a sequence of execution, and task would be executed sequentially in a way in which we have been designed it. And after the last task, the first task gets rolled over. That is what round robin kind of approach is being there. Okay, so in round robin approach, which is the most commonly used task for the time shared approach. So, or the time shared activities, we can make use of this particular round robin approach very easily, where the task joins first in, first out when it becomes ready for execution, and task at the head of this queue execute for most of the one time slice. Isn't it? The better example is time shared kind of activity. The better example is time shared kind of activity. So the head of this FIFO, head of the FIFO is referred to be as a priority at that particular time, and the time slice is being offered. Okay, and based on the time slice, the next task would be keep on executing. So the addition word that you can see here is a weighted round robin. The basic approach that happens to be, if you get to know, if you get to know the weights for a specific task in a round robin to be decided or to be a decisive in order to attain the final timeline of your execution, then you're supposed to offer the proportionate amount of time slice to that respective task. And this is an approach that we call to as a weighted round robin approach. How does it goes? This approach builds on top of the basic round robin scheme. Rather than giving all the ready task equal share of the processor, which happens in round robin, different jobs may get different weights. Getting this? And for example, if the task with a weight WT gets WT time slice with every round, and the length of the round is equal to sum of the weights of all the ready jobs. If, for example, in 1 second, you have to execute 6 tasks, for example. Okay. Now, these 6 tasks would carry the different weightage of sharing the CPU time in 1 second. Total has to be 1 second, but 6 tasks might share the different time, not as against of 1 second divided by 6, that is equal share as we found into the round robin. Okay. And these particular weights are to be decided, this to be designed a priori of its execution. These weights are to be decided in a priori of its execution based on the important activity a specific task might carry onto it. So decision of the weights, designing of the weights is the basic art or is the basic philosophy of, or the basic design task, more to say, for this particular weighted round robin approach. Getting it? So only the weightages are being added onto this basic round robin approach of it. For example, this particular approach might be well suited for scheduling of real-time traffic in high-speed switch network. Why? Because in high-speed switch network, you might go for the high priority packages to be offered with more amount of time to reside on the network. That even might be possible, isn't it? So you might need to prioritize the messages, and these messages you wanted to reside over the network so that the data integrity for that particular messages would not be compromised, being there to be as an high priority messages. So you are giving more weightages for existence of those kind of priority messages on the network. So there are a number of examples that you can definitely keep on thinking onto it. Okay, fine. So let's move on to the last part of this approach, which is priority driven approach. I think this priority driven approach is being talked even in the past also. When we discuss the micro COS to MUCOS to approach the scheduling mechanism, we say that high priority and ready to run is the task that must be running at any point of time. So priority based preemptive scheduling is being discussed. Okay. And let me take an opportunity to reiterate this at this particular time, that this particular priority driven approach is more popular, more common in design of real-time system, because as I said you, that every task cannot have the equal or the task prioritization is basically a key. As you go on granularizing this particular task to an finer level, priority that you are assigning to the n number of tasks, that becomes a crucial point in trying to meet the deadline of that particular application. And that is what we understand, that priority driven approach becomes a very high standard, or it becomes a very common approach, or which becomes a very famous approach for meeting of the deadline. What is it all about? The term priority that refers to the large class of scheduling algorithm that never leaves any resource idle intentionally. And the allied advantage that you would get it's not only just look onto the task, but also resources which grabs by the task are also not to be expected to be left out idle. Okay. And that is what because you decide the priority based on the importance of that, isn't it? So that's it. Scheduling decisions are made when events are such as release and completion of the task that occurs. That's what we call as a priority driven algorithms are event driven. And that's what you get to know. Like if you remember, we have seen the conjunctive synchronization, disjunctive synchronization, even the blend of conjunctive and disjunctive synchronization. We have AND synchronization, we have OR synchronization. So depending on the priority that you are defined for the task, in what way you wanted the further event, further activity to be driven off, that even decisions can used to be taken with the help of this kind of approach that we call priority driven approach of it. Okay. Then this particular approach would attempt to make the locally optimal decisions, and these locally optimal decisions would always be there in, even in a dynamic sense, in order to achieve the deadline that's what's your you have been designed for that applications. Okay, so there are n number of benefits, there are n number of allied factors, those are in support of priority driven approach in order to get this particular task to be met within a certain deadline. And that's what I iterate, that this is a famous approach that is being taken worldwide for design of the real-time systems. Design of the complex real-time systems or design of some moderate real-time systems are always being taken care by this particular approach, priority driven approach. Okay, and the resource sharing also becomes vital in this particular approach of it. Okay, so these are the three approaches that we need to understand. And commonly used approach, as I said you, in the real-time system design is this priority driven approach of it. Okay, then in the conclusion part of it, we can say that RTOS service mechanism is different than GPOS. So this, though the services are being offered as the same one, the mechanism is different. So service time of RTOS is constant, deterministic, and known a priori. Approach of scheduling is subjective to an application requirement. It decides efficacy of the design system. And the references, those were used of it, is the book Simon, the white paper that I was referring to this, okay, and this Liu book for understanding the common approaches for the scheduling of real-time systems. Okay, and this ends for the second part of this particular discussion. Okay, so I thank you everyone for joining this particular session.